Hi everybody. Today we're going to do 11.4 modular arithmetic. It's called, and well, let's get right down to it. I'm going to share my screen with you because I love to share. And here we go. So actually, let me make it a little bit bigger so I can see better. Okay. Very nice. Is it left fit? Ah, yes, beautiful, beautiful. Okay, so modular arithmetic. So there's a when we talk about numbers being congruent modulo n, that means that if modulo, well, if you think of a clock, right? So, at 2 o'clock, the hour hand is on the 2. Well, 12 hours later, the hour hand is also on the 2. 48 hours later, the hour hand is also on the 2. Because, the clock goes around and around. Is that a good example? How about a better example? At 1:05, I'm going to restart this. No, I'll leave it here. At 1:05, the minute hand is on the 5. An hour later, the minute hand is on the 5. In fact, as long as I'm 5 minutes past an hour, the minute hand will always be on the 5. So if we're just looking at the position of the minute hand, it doesn't matter whether it's 1:05, 2:05, 3:05, 4:05, 11:05, it doesn't matter. Similarly, if we're looking at mod 5, so if all we care about is the remainder, the leftover, right? Because 1:05, that 5 minutes is left over. So let's say we talk about modulo 5. I'm looking at just numbers, multiples of 5. So 13, if I divide 13 divided by 5, I get a remainder of 3. If I divide 38 divided by 5, I also get a remainder of 3. Well, as far as modulo 5 is concerned, if I had just a wheel, with numbers 1 through 5, then as long as 13 and 38 would wind up being in the same spot, they'd be in the 3 spot. So that's what I'm trying to say. It's kind of like think of it as like an old a clock, now they call it analog clock. When I was a kid, it was called a clock. Now it's called an analog clock because that's what happened. And there's an expression. I don't know if you heard that. Something called a retronym. Like when I was a kid, it was called television. Now it's called black and white television. You know what I'm saying? Or pictures. Now they're calling black and white pictures. Or a clock. Now it's called an analog clock as opposed to a digital clock and so forth. Anyway, it's called a retronym. Meaning we didn't call it black and white TV. We didn't call it, analog clocks. But now, in retrospect, they called that. Anyway, so 13 minus 38 is negative 25, which is a multiple of 5. So that's what we mean when we say something is congruent modulo n. Let's see what happens. What's going to happen when I click over here? What's going to happen? Oh, look at that. So here's the definition of congruence modulo n. If n is a positive integer and n is greater than or equal to 2, then we define congruence modulo n to be the relationship. Now notice it's like an equal sign, but there are 3 things instead of 2 things. 3 lines instead of 2 lines. And they stick the n there because congruence depends on what the modulo is. So it could be mod 5, mod 7, whatever. So it's defined on the integers by a is congruent to b mod n, means that n divides a minus b. And another way of saying that is to say that if I would take a divided by n, I get the same remainder as if I do b divided by n. It's just another way of saying it. Now I got it. Now how do I jump back to where I was? Can I jump? I'll have to go like this. I was on page 279. Okay. So now modulo addition. So A plus B modulo n, that's how we read it, is the remainder after A plus B is divided by n. That's how we define modulo addition. So 7 plus 12 mod 5, well, 7 plus 12 is 19. The remainder, if I divide by 5, is 4. So 7 plus 12 is equal to 4, is congruent to 4, modulo 5, mod 5. And multiplication is defined the same way. 7 times 4, which is 28, is congruent to 3 mod 5. Because I take 7 times 4 and I multiply that by I get 28. If I would divide 28 divided by 5, I get a remainder of 3. Now notice also, I just want to point something out here. Let me just get sort of point this out. I'm just following this. I'm going to close. By the way, if you notice that when you on the YouTube videos, it'll say scroll 245 and it'll say SU 21. Now I got rid of the SU 21. Ignore that. Just don't worry about it. Anyway, so I just want to make a point here that if you have 7, I don't know how to do congruence. I guess I could if it was 7 times, that's a modulo 5. Times 4. So on the other hand, 7 is the same thing as 2. And 4, well, 4 is the same thing as 4, I guess. Modulo 5. And let's see what that is. Well, we explained that, let me do an insert. And I'm going to say congruent. Let's see if congruent. No. It's got to be, this is like every. Integral to sounds better. So this is congruent. This is congruent to 3, but 2 times 4, which is 8, is also congruent to 3. In other words, so why is that? Because 7 times 4 equals 28, and 28 divided by 5 as remainder 3. Whereas here, 2 times 4 equals 8, and 8 divided by 5 as remainder 3. So it's kind of like, it's kind of like, yeah. And that's going to be the story. Similarly, let's just keep this mod 5. It's pain just doing this. I'm just gonna change the numbers here. 7 times 6. That's going to count into 2 because 7 times 6 is equal to 42. And 42 divided by 5 has a remainder of 2. And here, similarly, So 7 is counting to 2, and 6 is counting to 1. And this is just 2 divided by 5. So notice that 7 is counting to 2, 4 is counting to 4. 7 is counting to 2, 6 is counting to 1. So if I multiply, no matter how I do it, I'm going to want to get the same answer. So that was really my whole point here that I wanted to point out. Okay, back to the book. So now whenever I do modulo n, I'm basically getting a number. If I'm dealing with mod 5, the numbers I'm going to get is 0, 1, 2, 3, 4. 5 is already 0 again. So my number is going to be 0, 1, 2, 3, 4. So when I do mod 5, those are the numbers I'm always going to get. And this here is what I just demonstrated, kind of in that in the little Google Doc. We use the notation Zn to be modulo n. So Zn is the numbers from 0 up to n minus 1. So Z5, we were just dealing with Z5. Oh, Z stands for integers. Why does Z stand? Why does Z stand for integers? That was one of that. I'm guessing there's probably some. That's probably to say. Why does Z stand for integers? Zahlen, if I'm pronouncing it right, is a German word for numbers, and that's just what a lot of letters that we use, like M stands for slope, because in French, that's the word for a slope, and a lot of times there are letters. What does Q stand for? Rational numbers. It's also something I always wondered. So a quotient, interesting. I never thought of that one, because a rational number is a fraction, so it's a quotient. Oh, I never knew that. Huh, like that. Look at all the things you learn in college. Anyway, let's go back here. So we have our first. Now we're going to just go to our first theorem here, which is that I'm going to get I'm getting in the way here. Okay. I like keeping this up here, so you see that it's really me talking to you. I'm an actual human being. I actually exist. Sometimes having this here gets in the way a little bit. Something gets in the way a little bit, but it is nice just to see that I'm like a human being. That I'm really here. Anyway, if by the way, we're getting it's a very exciting time in Hogwarts now, because this we're having the Tri-Wizard tournament soon, which is very exciting, very very exciting and different. It doesn't happen. It's not every day that you have that. Anyway, so if A is part of Zn, so it's one of those numbers, and assuming A doesn't equal 0, then the additive inverse of A is n minus A. And that's easy to prove, because A plus n minus A, well, that's just n, and n is counting to 0. And since n is equal to n times 1 plus 0, that means A plus n minus A is 0. Sometimes the proof is more complicated than just to simply, that's the way it is, and that's to be proved rigorously. Anyway, I digress. So modular addition is definitely commutative. It's definitely associative. 0 is the identity element, and every non-zero element has an additive inverse. So I guess you could say 0 is its own additive inverse. So really, every element has an additive inverse. So to put it into the language that we've been doing so far, that means that Zn with modulo addition is actually a group. It satisfies all the conditions of a group, and that's why it's so interesting to us here in this realm. Not just because it's of the attributes of modular addition, but the fact that it does form a group. Now, what about anyway? Let's define it here. So the additive group of integers modulo n is a group. The domain of the group is 0 to n minus 1, and the operation is modulo addition. But what about modular multiplication? Will that form a group? Well, that's interesting because let's just see. The answer is sort of. By the way, sort of is a very funny word because usually sort of doesn't mean that much, but sometimes sort of can have devastating consequences. Like if I say, if the doctor says you're going to live, sort of. Anyway, multiplication mod n is also going to be commutative and associative, and the algebraic properties of addition and multiplication, mod n, are the same as for just regular addition and multiplication. But you can't make a group out of it because 0 will never have a multiplicative inverse. In other words, I can never multiply anything by 0 and get I can never multiply anything by 0 and get 1. So it won't be a group, but there's kind of a way that we can make a multiplicative group. And what that is, and this is, we're going back to our famous, well, let's just take a look. The multiplicative group of integers modulo n. So if I look at the numbers, the numbers k in Z, where k is between 1 and n minus 1, and the GCD of n and k is 1, and I'm using the operation of modulo multiplication, then I do get a multiplicative group modulo n. In other words, whatever the mod is, I'm looking at all the elements which are relatively prime. So let's say, for example, let's just do an example right here. The book's going to give us an example. Let's say we want to do Z12, looking at mod 12. Okay, and mod 12 is something that we actually, again, that's what clocks are, So the days are counted military. So if someone started a 4-hour trip at hour 21, so he'd arrive at the hour 1. 21 plus 4 is congruent to 4 mod 12. So he'd arrive at hour 25, which is the same thing as hour 1. So if a satellite starts its first orbit orbits the Earth every 4 hours and starts the first orbit at hour number 5, so it would end the first orbit at hour 9. It would end the 10th orbit at 5 plus 10 times 4, which is 5 plus 40, which is 45. But 45 modulo 24 is 21. Because if I do 45 divided by 24, I get a remainder of 21. And let's I want to, okay, so let's, okay, so let's okay, so I want to go back to this here, and let's talk about integers mod 12. So let's open up a little spreadsheet. Okay, so I'll open a little spreadsheet, and we're doing here let's make this a little bigger. So mod 12. So we have, what are the integers? What are the numbers? So we're going to do multiplication here. And it's mod 12. The x here means multiplication. So in mod 12, we have 1. Now 2 is not relatively prime, 3 is not relatively prime, 4 is not, 5 is, 7 is, and I think 11, is that it? Anything else? Let's just make sure we got this right here. 2 and 3 go into 12, right? 2, 3, 1, 2, 3. 4 is also goes into 12. 6 goes into 12. 7, 8. 8 has a 2. 9 has a 3. 10 has a 2. 11 is not. And okay, so over here I have 1, 5, 7, and 11. And let's just make these. And let's see. Okay, so 1 times 1 is 1. 1 times 5 is 5, 7, and 11. That was easy. Now 5, and we can go down this way, 5, 7, 11. Now, okay, 5 times 5 is 25. A 25 mod 12, 25, that's 24 plus 1, so it's coming to 1. 5 times 7 is 35. Well, 36 is the multiple of 12, so 35 is coming to 11 mod 12. And 5 times 11 is 55. Let's see, 40, from 48 to 55 is 7. And of course, that's a, notice the symmetry here, or the, because that's a 7. 7 times 7 is 49, but 49, that's 1 more than 48, so it's the remainder of 1. 7 times 11 is 77, and 77 is 77. Okay. 77 is, well, 12 goes into 72, so it's 5. And of course, again, that's going to be 5. And 11 times is 121, which is 1 more than 120. So, pal, there we go. And that's our, there we go. Let's make this, I want to just have this consistent with other, that's good enough. Alrighty. I'm going to take this here. This is our modular arithmetic, and I'm going to put this into our spreadsheet. So what we see here, and this is really my point, is that the integers mod 12 forms a group under multiplication. But it's not using the numbers 1, 5, 7, 11, which are relatively prime to 12. By the way, a number which is not relatively prime also won't have a let's see, won't have an inverse. 6 times. Yeah, a number which is not relatively prime will not have a multiplicative inverse, like 8. There's no multiple of 8, which is going to be 1 more than a multiple of 12. There's no multiple of 3, which is going to be 1 more than a multiple of 12. So the numbers which are not relatively prime are going to be all messed up. But anyway, this is a nice example of that. Well, that concludes 11.4. It's been loads of fun, and we'll see you guys next time. Bye. Are you sure you want to stop?